In 1952, in a basement office at Columbia's Lamont Geological Observatory, Marie Tharp unrolled a sheet of graph paper and began turning columns of ship soundings into a cross-section of the Atlantic Ocean. What appeared on the page was not supposed to be there. A deep, continuous notch running down the middle of an underwater mountain range. The seafloor, at that point, was still treated as a mostly settled blank. Mud, basins, isolated ridges, mapped in fragments by ships passing overhead. Tharp was not at sea. She was not operating new equipment. She was drawing. But the drawing revealed a structure large enough to split an ocean basin. This is a story about a map that stopped being a picture and became evidence. To understand why that matters, you have to understand what the ocean floor looked like to science in 1952. Not what it actually looked like, what science thought it looked like. The answer was, not much. Before the Second World War, depth measurements of the deep ocean were scattered and sparse. Ships would lower a weighted line over the side, wait, pull it back up, and record a single number. That was a sounding. You might get a few dozen per voyage. The ocean covers 71% of the Earth's surface, and most of it had never been measured at all. Echo sounding, bouncing pulses of sound off the bottom and timing the return, had existed since the 1920s, but its coverage was fragmentary. The existing maps filled the gaps with guesswork. Smooth basins, gentle slopes, a few isolated seamounts. Scientists already knew a broad, elevated feature ran down the middle of the Atlantic. What they did not know was what it actually looked like, whether it was smooth or fractured, passive or active, dead geology or something still in motion. The war changed the instruments. The Navy needed to understand the seafloor because submarines were using it, hiding above it, navigating around it, dying in it. Wartime pressure made echo sounders faster, more sensitive, and standard equipment on military and research vessels. By the late 1940s, oceanographic ships were generating something that had never existed before: dense, continuous depth profiles of long stretches of ocean floor. Not point measurements, lines. The problem was that nobody had yet turned those lines into a coherent, large-scale picture of the seafloor's shape. The data existed. The synthesis didn't. Marie Tharp arrived at Lamont in 1948. She had a master's degree in geology from the University of Michigan and additional coursework in mathematics at the University of Tulsa. She had wanted to do field work. The expeditions run by Lamont's director, Maurice Ewing, didn't take women. It wasn't a formal rule, it was just how it was. Women stayed on shore. So Tharp worked on shore. Her job, paired with a geologist named Bruce Heezen, was to take the sounding profiles from Lamont's research vessels and assemble them into something coherent. Heezen went to sea and collected the data. Tharp stayed in the office and processed it. The division of labor was not subtle about its hierarchy. But the processing proved scientifically decisive. What Tharp was doing required something that wasn't, at the time, valued as scientific work. She wasn't running experiments. She wasn't writing theoretical papers. She was sitting at a drafting table, plotting depth values onto graph paper, column by column, profile by profile, trying to understand how those profiles related to each other across hundreds of miles of open ocean. The North Atlantic was the focus. Lamont ships had crossed it repeatedly, and Tharp had 6 parallel profiles running roughly east to west. 6 narrow slices through the same ocean basin at different latitudes. She began rendering them, and in each one, there it was, a notch. Not a smooth valley floor, a V-shaped cleft, sitting at the crest of the mid-Atlantic ridge. 6 times, in 6 different profiles, running all the way down the spine of the ridge. She called Heezen over. His first response, according to Tharp herself, was that it was girl talk. The dismissal matters. Not just because of what it says about how Tharp was treated, though it says that clearly enough, but because of what it reveals about the intellectual stakes. There were legitimate scientific reasons to be cautious. The profiles were few. Soundings could be misread. A notch in 6 cross-sections could be a local feature, an artifact of interpolation, a coincidence of topography at those particular latitudes. Skepticism was defensible. But the phrase Heezen used wasn't the language of scientific caution. It was the language of a conclusion reached before the data had been examined. Because what Tharp was describing, if it was real, was a rift valley. A place where the ocean floor was being pulled apart. A crack in the crust of the earth, running continuously for thousands of miles down the center of an ocean basin. That was not what the seafloor was supposed to look like. The dominant view among most geologists, including Heezen himself, was that the ocean bottom was static, stable, old. Continental drift, proposed by Alfred Wegener in 1912, had been dismissed by most of the geological establishment for decades. The seafloor was background, not mechanism. It wasn't doing anything. A rift valley would mean the opposite, that the seafloor was actively splitting, that something was driving the crust apart, that the ocean basin itself was, in geological terms, alive.
So Heezen looked for a reason to discard the finding. He spent the better part of a year being skeptical.
What changed his mind wasn't an argument. It was another data set. Lamont researchers had been compiling records of earthquake epicenters on the ocean floor, and the pattern was strange. The earthquakes weren't scattered randomly across the basin. They ran in a narrow belt, a continuous line through the middle of the Atlantic, roughly following the crest of the Mid-Atlantic Ridge. Tharp placed the earthquake map next to her Rift Valley profiles. The epicenters lined up with the cleft. An earthquake belt running along a rift zone wasn't just suggestive. It was mechanically coherent. Rifts produce earthquakes because crust is being stretched and fractured. If you were going to predict where ocean floor earthquakes should concentrate, given an active rift, you would predict exactly what the data showed. The two datasets had been independently derived. Neither had been built to match the other. And they matched. Heezen stopped calling it girl talk. If this kind of story interests you, science done in the margins, evidence that took decades to land, we cover overlooked discoveries like this every week. Subscribe so you don't miss the next one. But the story doesn't move cleanly from resistance to acceptance. That's not how paradigm shifts work, and Tharp's career is a good illustration of why. Heezen and Tharp's Rift Valley work was formally presented at the 1956 meeting of the American Geophysical Union and reached full publication in their 1959 monograph, co-authored with Maurice Ewing. The scientific community's response was divided, and in some corners, actively hostile. The rift hypothesis was tied to continental drift, and continental drift was still regarded by many as fringe geology. Several prominent oceanographers rejected the interpretation outright. Some argued the notch was a local feature, not a continuous structure. But Tharp kept mapping. She didn't stop at the Atlantic. The Mid-Atlantic Ridge had been suspected to extend into the Indian Ocean and Pacific. If the Rift Valley was real, a structural feature of an active seafloor rather than a local anomaly, it should appear in other basins too. Tharp worked through the accumulated sounding records for each ocean in turn. The same feature appeared, again and again. A ridge with a central valley, a rift. The same shape, scaled to each basin, continuous. What was taking form on Tharp's drafting table was not a series of disconnected local features. It was a single connected system running through every ocean on Earth. A submarine mountain range more than 60,000 kilometers long, longer than any surface feature on the planet. Slow-spreading ridges, like the one running down the Atlantic, had a deep, prominent rift valley at the crest. The shape varied with spreading rate, but the system was global and it was coherent. No one had seen it whole before because no one had drawn it all at once. In the years that followed, Tharp and Heesen worked with an Austrian panoramic landscape artist named Heinrich Baran to translate the depth data into a visual form that could communicate the shape of the entire ocean floor. The goal was not decoration. It was comprehension. A rendering precise enough to carry scientific information and accessible enough to reach people who would never read a bathymetric contour chart. This is where Tharp's work crosses into territory that is genuinely harder to place. The maps produced with Baran were not measurements in the narrow sense. They were interpretations, informed, rigorous, evidence-constrained, of what the seafloor would look like if you could drain the ocean. That distinction was where the dismissal was easiest to land. Critics who wanted to question the rift hypothesis could point to the maps as illustrations rather than data. Artistic renderings, not science. The fact that Tharp was a woman working in a support role made that dismissal easier to sustain. Her drafting table looked, to a certain kind of observer, like exactly what it was, a drafting table. But the maps weren't built from artistic intuition. They were constructed from depth profiles, continuous echo-sounding measurements taken across thousands of miles of ocean. The visual form was new. The information content was not. And the information content was about to become impossible to ignore. In a manuscript circulated around 1960 and formally published in 1962, a geologist named Harry Hess proposed a mechanism for what Tharp's maps were showing. The term that entered the literature, coined by the geologist Robert Dietz in 1961, was seafloor spreading. New crustal material was being generated from the mantle at mid-ocean ridges, pushing the existing seafloor outward in both directions. The Rift Valley was the site of creation. The ocean basins were not static floors. They were conveyor belts, slowly carrying material away from the ridge, and at convergent margins, back into the earth. It was the mechanism that continental drift had always lacked. Wegener had described the motion of continents without being able to explain what was moving them. Seafloor spreading explained the engine. And the engine was sitting in the middle of Tharp's maps, marked by a continuous valley she had been drawing since 1952. Strong confirmation came in 1963, when Frederick Vine and Drummond Matthews, and independently Lawrence Morley, published their analysis of magnetic striping on either side of the mid-ocean ridges. Symmetric bands of magnetized rock, recording reversals of the Earth's magnetic field, preserved in the basalt as it cooled and spread outward from the ridge. The stripes matched on both sides. The seafloor was spreading. The data was there for anyone who looked, but looking required knowing where to look. The knowledge of where to look came from the maps. Plate tectonics, the framework that now underlies every field of Earth science, from volcanology to seismology to our understanding of earthquake hazards, was not a single moment of discovery. It was built from converging lines of evidence through the mid to late 1960s, each one reinforcing the others. Its primary visual foundation was a map of the seafloor drawn by a woman who was not allowed on the ships that collected the data she used. Think about what that means. Tharp and Heesen's World Ocean Floor Map was published in 1977, one of the most reproduced physiographic depictions of the ocean floor ever made. It appeared in textbooks, journals, and on classroom walls. It is almost certainly the image of the seafloor that most people educated in the late 20th century first encountered. Heesen died that same year of a heart attack aboard the research submarine NR-1, not long after the map was published. Whatever his private understanding of how the work had been divided, he had not made it explicit in print. His name appeared first in the published record. Tharp's role was legible to anyone who knew to look for it. Most people didn't look. Tharp received the first Lamont Doherty Heritage Award in 2001. The citation described her as a cartographic pioneer. She was 80 years old. She died in 2006. The word cartographer is accurate. It is also incomplete. Tharp didn't trace a landscape that already existed clearly in the literature. Working from profiles that had been sitting in filing cabinets for years, she produced the first coherent image of the global mid-ocean ridge system, a 60,000-kilometer submarine mountain range whose shape, continuity, and active rift structure no one had previously assembled into a single, legible picture. Other scientists had pieces of it. Tharp made it visible as a whole. The discovery was the map. Not the data the map was made from, and not the theory the map eventually supported. The act of drawing, the synthesis, the interpretation, the decision to keep rendering profiles when the results kept contradicting what the field believed, that was the scientific contribution. The image was the instrument. Science has a settled story about how discoveries happen. Hypothesis, experiment, result, publication, credit. That story struggles with the kind of work Tharp did, because her contribution didn't fit any of the recognized categories. It wasn't a hypothesis, it wasn't an experiment, it was a representation, but one so information-dense, so carefully constrained by evidence, and so far ahead of the available theory, that it functioned as something closer to a proof. The difficulty of placing that kind of work is part of why it gets undervalued, and the undervaluing is not random. It has historically concentrated among people already positioned outside the recognized centers of scientific production. The people doing the synthesis, the compilation, the rendering, the work that turned raw data into something a field could actually use. Rosalind Franklin spent years producing some of the most precise X-ray diffraction images of DNA ever made. The image that helped Watson and Crick build their structural model was shared without her knowledge. She was not included in the Nobel Prize awarded in 1962. Cecilia Payne established in her 1925 doctoral thesis that stars are composed primarily of hydrogen and helium, a conclusion her senior colleagues initially pushed back on as implausible, and that was only gradually accepted as independent evidence accumulated. The people who confirmed these findings received the formal recognition. The people who made the findings possible were filed under support work. The common thread is not gender alone, though gender is part of it. It is a persistent institutional confusion about which parts of the scientific process count as discovery. Data collection counts. Theory counts. What happens in between, the translation of raw measurement into something that reveals structure, tends to get filed as technical rather than intellectual, as assistance rather than authorship. Tharp's drafting table looked like support work because the science of the 1950s had a clear idea of what discovery looked like. It looked like a man on a ship. What the seafloor actually looked like, it turned out, was something else entirely. It looked like what Tharp drew. If you want to see more stories like this one, the discoveries that almost weren't, the work that got filed away, subscribe to Nobody Noticed. We find these things so you don't have to. Thanks for watching Nobody Noticed. See you next time.